Right, so this is the energy balance that you apply for closed thermodynamic system, or in fluid mechanics we call it control mass. They are same, right? So we are using the only one terminology. So this internal energy can be approximated. So let's say we approximated it as a function of temperature only. So that this one become mCVT, right? So we have the mass of the fluid particles. So the mass of the fluid particle, this fluid particle have the value of CV. CV is a specific heat at constant temperature, a constant volume, because V here tell us about volume. Constant specific heat at constant volume. The unit is joule per kilogram. And then we have the temperature, right? So in the development of Bernoulli equation, we said that the initial temperature here T, and that value of T at the final position, the temperature is same, right? So we said T initial will be equal to T final. So this has an implication and understanding about our flow, that the flow is isothermal. So this is engineering assumption in development of Bernoulli equation. It is also an isothermal flow, so that this one can be neglected, right? So we're going to neglect this term. So we have only kinetic energy, only the potential energy. So kinetic energy has definition. Ke is equal to half m, because we are considered closed thermodynamic system or control mass. So we have mass there. The unit will be in kilogram, right? And then we have the velocity. So as I said, we are evaluating as component system, as coordinate system. So this one is a resultant velocity. It's not a component, but a total or resultant velocity. So in our fluid mechanics, this one will be the average velocity. And then we have, if we have a change of kinetic energy, so this one mean that half m v minus v power of 2. So we want to know how we can evaluate these values, right? Because definition of this change will be according to the practice, right? We have this final minus initial, so that should be the definition, right? So whatever work being done, it will cause the fluid to change, right? So the final minus the initial, so this is what should be done. And then we have this potential energy, PE. This one will be mg z, right? So what is z? So z should be determined from the direction of gravity. So we need to know about gravity. So and from there we can determine the coordinate system. So let's say this one is z. This one is z equal to 0, and z is certain values, right? So z. So when we talk about the data change of kinetic energy, potential energy, This one will be equal to m g, and then we have z final minus z initial, mula akhir, right? Final and initial. But when we derive this equation, we have to remember that we have this integration part, right? So it's better to have a different notation for this our problem here, right? Especially when we evaluate this term. So how we can put that in the term that we can evaluate dia punya expression. So this one is much more easier. This one will be z plus dz minus z, right? So we have at this position, let's say we have z, this one z plus dz, right? So this is the final minus the initial position. So we can then have dz. And what about this one? So this one will be don't ask me how I can get this one. You can find the proof. So will be the integrations of m v dv, right? So that will be the what is the unit? Oh yes, so this one it will be in joule. So we have evaluated from z, this one will be evaluated from the average velocity. This one will be the volume. So we have the integration of velocity dv plus when evaluated for v, this one will be z, and m g dz. This one is equal to p a v is
Doctor, the screen is small.
huh? sorry. Saya terlupa. Sebab saya tak buka aircon kan, panas kan. Bagi saya buka aircon jam. Sorry, PA DA. We can convert the volume sama juga dengan m divided by rho, right? M divided by density. So we have P we going up, right? So normally if we going up from a location of fluid where the mass is larger, so we have large of pressure, right? And then we go up, there is less molecule of mass, so we expect less pressure, right? So using that hypothesis, we say that the final pressure is less minus P plus dP, right? So this the final values minus the initial values, and then we have this m per rho, right? So this one is equal to m per density, and then we have dP, and we're going to evaluate it with P, right? Sorry, we have minus there. Okay, now we have mass here that we can place outside, right? Because does not change. Here mass is also there. and gravity is always constant, so we have that a form. So we can cancel the mass, right? And then we can place the right hand side to the left hand side. So we have P 1 per row dP plus V average value, changes of average value, plus sorry yes the Z is 1 by G dz Z. Itulah kan. So V, this one is equal to 0. So when we do integration later, we're going to have a constant value here. Okay, right, with the variable that we have there, we have P divided by rho, and then we have V power of 2 divided by 2, and this one we have G Z, right, and this one will be constant. So if we place a limit for our integration, we can find that this one should be your total pressure, right? Because the whole equation here, sorry, not the P total but by density, right? So we have total pressure